Hello and welcome to our lesson on Hess's law. We just got done talking about calorimetry in the last lesson, so today we're going to talk Hess's law and how energy plays out in all of that. So we're looking at energy in delta H, which is enthalpy. So enthalpy is well known for many reactions, and it's inconvenient to measure it for every reaction that we are interested in. So we can just look it up. We can estimate it though using published values and properties of enthalpy, and so Hess's law allows us to do that, and we're going to look at how that kind of works here in a second. So according to Hess's law, if a reaction is carried out in a series of steps, so A plus B plus C, delta H, your change in enthalpy for the overall reaction, so for A plus B plus C, is going to be equal to the sum of the enthalpy changes for the individual steps. I wish that we could still come up with ideas like this that were pretty straightforward. But if the reaction in A has a certain amount of energy, and B has a certain amount of energy, and C has a certain amount of energy, if I add all those up, my change from A to C is going to be the same as those three steps. And so, for example, on the left you see a delta H value of negative 890 kilojoules when you burn, looks like methane and oxygen produce carbon dioxide and water. In this, the delta H of the first step is negative 607 kilojoules, and for the second one is negative 283 kilojoules, and if you add those together you get negative 890, and that's what Hess's law tells you. So because delta H is a state function, the total enthalpy change depends only on the initial state and the final state of your reaction. So it only depends on the reactants and products at the very end of the reaction that takes place. So enthalpy of formation, this is what we can find in our textbook as different values, but you have an enthalpy of formation is your enthalpy change for the reaction in which a compound is made from its constituent elements. So when your reaction elements come together to form a compound, that is going to give us our enthalpy of formation, or our delta H. And so for example, water is H2O. So when H2O forms from hydrogen and oxygen, you have a certain amount of energy, and that's your enthalpy of formation. That's your delta H sub F, which you can find in almost any chemistry textbook or online if you want to. Here are some standard enthalpies of formation. So some ones that are real easy to look at are these guys, and these are all at 25 degrees Celsius and 1 atmosphere of pressure. So these are your enthalpies of formation. I apologize for the blurriness of the screen, but you have access to a textbook, or you can get this online, which will give you the values. So all of these substances have enthalpies of formation. And so when we go from reactants to products, we can look at how much it took to get there, and we can ignore the intermediate steps because of that. If you are calculating delta H, so this is what we're going to look at here today. This is Hess's law kind of in action. For this reaction of propane, which is C3H8 plus oxygen producing carbon dioxide and water, we're going to imagine this as occurring in three different steps. So step one is you break down propane into its constituent elements, its basic parts. So we break down C3H8 into 3 carbons and 4 hydrogen gas molecules. So these 3 carbons bonded to these 8 hydrogens were split into just carbons and hydrogens. That's step one. Step two is going to be the production of CO2. So we took those 3 carbons from step one and we added them to 3 oxygens, which were present up here, and we have 3 carbon dioxides now. That's step 2, which gives us our 3 CO2s over here. So the only last thing we have to do is I still have 2 oxygens I haven't accounted for, and I still have 8 hydrogens, where I have 4 H2s instead of 8 hydrogens. So I have 2 O2s and I have 4 H2s. And so that means step 3 is going to be to take those 4 H2s and 2 O2s, these guys here, and make 4 water molecules out of the deal, which is filled in right here for water. That's our third step. So this reaction, which looks like a single propane plus oxygen becomes carbon dioxide and water, can be split into 3 separate steps. And those 3 steps all have their own enthalpies of formation. So to calculate delta H, we're going to take these 3 steps down here. So all of those 3 steps have their own enthalpies of formation. We're going to take those individually and look at them. And so if we scroll down a little bit, actually jump to the next slide. So because of this, we took propane here and split it into 3 carbons and 4 hydrogens. On this side, I took my 3 carbons plus 3 oxygens and produced 3 carbon dioxide. So because C is here, 3 carbons are here and 3 carbons are here, I can get rid of them. I have 3 O2s on the left. I don't have anything yet to cancel that out. And then my last step, I had 4 hydrogens here, which match the 4 hydrogens here, paired with 2 oxygens to produce 4 water molecules. So if I write down everything I have left, I have C3H8, which is written here. I have 3 O2s plus 2 O2s, which gives me my 5 O2s, which is there. On this side, I get 3 carbon dioxides, and I get 4 water molecules. So that is Hess's law kind of in action. We take those 3 separate steps, put them together, and I get my total reaction total products. And then we can calculate delta H. So using Hess's law, we can take, so this sigma sign means the sum of, N stands for your stoichiometric coefficients or your molar ratios, and then delta H is the enthalpy of formation of your product. So for each product, we take it times its stoichiometric coefficient. And we do the same thing, the sum of M, which is another stoichiometric coefficient of the enthalpy of formation of your reactants. And we're going to subtract those 2, and that's going to give us our change in enthalpy. So if we use our enthalpies from the table, so either out of a textbook or on the internet, should all be the same. You can find the enthalpy of formation of propane is going to be negative 393.5 kilojoules. And because I have, that's my carbon dioxide, I apologize. So products minus reactants. So as carbon dioxide, I have 3 of those. To form carbon dioxide, it requires the loss of 393.5 kilojoules. And I formed 3 moles of it, so there's my 3 out front. I have 4 water molecules. Enthalpy of formation of water is negative 285.8 kilojoules. So that makes up for my 4 water molecules. I'm going to subtract. Enthalpy of formation of propane is negative 103.85 kilojoules times 1, because that's my coefficient out in front. And then because oxygen is in its elemental form, so oxygen by itself under standard conditions is a gas. Because of that, the enthalpy of formation is always going to be 0. So 5 times 0 is going to be 0. Then you multiply all these together. So 3 times negative 393.5 gives you negative 1,180.5. 4 times negative 285.8 gives you negative 1,143.2. I'm still going to subtract 1 times negative 103.85 is negative 103.85, and then 0. So I'm going to combine these 2, add them together. A negative plus a negative gives me a big negative number, which is negative 2,323.7 kilojoules. Subtract a negative, so I'm going to add this to it, which is going to give me a final enthalpy of formation, final change in enthalpy, I guess. Not formation, just final change in enthalpy of negative 2,219.9 kilojoules for the combustion of 1 mole of propane in the presence of oxygen. That is Hess's law, is stepping you through those calculations there. I will provide you a practice worksheet so you can do some practice with this, but that's what you're working with. You're adding up step 1, step 2, and step 3, and putting it all together to give you your final outcome here. One last little bit is we can use, we get fuel from the energy and foods we eat. So a little bit different than burning something, I guess at least burning it in oxygen. but we use food for the same purpose. And so your carbs have 17 kilojoules, provide 17 kilojoules of energy per gram. Fats provide 38 kilojoules of energy per gram, and proteins provide 17 kilojoules of energy per gram. If we're talking calories, it's 4, 9, and 4 respectively. These substances here, so these are your three basic substances. That's where we get most of our fuel in food. It comes from carbs, fats, and proteins. These substances here are showing you kind of what they're made of. So there's this many grams of carbs, or this percent of carbs, this percent of fat, and this percent of protein. And you can calculate energy accordingly. But these are just the straight, the pure substances that we're looking for. So if we look at this, we can then look at energy and fuel. So that's foods, that's what we eat. And you'll have to do some practice with that. This is looking at fuel. So for example, we burn all sorts of fuels. Everything from, say, wood to coal, which is these two. We use charcoal, we use crude oil, we use gas, natural gas, and then a not so common form, but a very powerful one is hydrogen. And so this tells you its makeup, percent composition by mass, carbon, hydrogen, and oxygen of each different fuel source. And then on the right is your fuel value, or your kilojoules per gram of fuel. So for every gram of fuel, how much energy are you getting? And if you notice, we get 18, 31, 32, 34, 45, 48, 49, decent numbers. And then you look at hydrogen. Hydrogen gives us 142, oops, I screwed that up, 142 kilojoules per gram. That's incredible. Hydrogen is the kind of apex of the fuel industry that we are all forever trying to mimic and catch up to hydrogen and produce that kind of energy. Because to go along with that, there's no emissions when hydrogen burns. H2 plus O2 produces H2O. So there is no carbon dioxide. There is no pollution. It is strictly water being pulled out of there. And so that's the ideal, that's the goal with the fuel industry and energy production, is to get to that point. Some other sources. Ooh, I lost my slide. That's a bummer. I guess we're going to end it there. Ooh, maybe not. There we go. Some other sources. So I can't write on this page, but that's okay. We use processes like nuclear fission, which produces 8.5% of our U.S. needs. We have other renewable energy sources, such as solar, wind, and geothermal. And that's this little segment here. I wonder if I can write on this. Nope. This little segment up here, which is renewable energy, is our renewable energy sources. But those are energy sources. And again, the goal is hydrogen and hydrogen's efficiency and power. Until we get there, we'll keep trying. But that is Hess's law, and let's look at a little bit of a look at energy. We'll do some practice with that as well. Thank you guys for watching, and I will talk to you next time.